When computer scientists proved exact solutions to NP-complete problems are impossible to find efficiently, they turned to a viable workaround, approximation. To establish the hardness of these original problems, researchers relied on standard Karp reductions. The mechanics of a Karp reduction are designed for exact decision boundaries. It transforms an instance of one problem into an instance of another, so that a yes answer maps perfectly to a yes answer. But this rigid mapping hides a structural flaw. Karp reductions are entirely blind to the quality of a solution. If you take a 3CNF Boolean formula where 99% of the clauses are satisfiable and run it through a standard reduction to the maximum clique problem, the resulting graph might yield a maximum clique that represents a drastically smaller fraction of the whole. This unpredictable collapse means you cannot guarantee that a near-perfect solution in the starting problem translates to a near-perfect solution in the target problem. Tracking exactness tells us nothing about the bounds of proximity. Standard reductions fail to map approximations entirely. To solve this mapping issue, theorists had to discard the idea of continuous quality metrics and create a shattered space. They engineered a specific structural solution, the gap-producing reduction. This animated diagram shows how a gap problem is constructed. We first establish a rigorous upper threshold, alpha, marking instances with a high-quality optimum. Next, we establish a strict lower threshold, beta. The space between alpha and beta is mathematically voided out. This gap guarantees that all instances produced by the reduction will fall exclusively into the extreme high zone or the extreme low zone. There are no inputs that yield an optimum in the void. This creates a trap for any approximation algorithm. If an algorithm can approximate a solution with an error margin tighter than the ratio between alpha and beta, it instantly distinguishes the high instances from the low instances. By forcing an approximation algorithm to leap this mathematical void, the gap reduction forces it to solve the underlying exact NP-complete decision problem. Efficient approximation becomes mathematically identical to solving P equals NP. To actually build this gap, complexity theorists shifted their focus away from optimization graphs and looked at the mechanics of proof verification. Consider the flow of information when a verifier checks a mathematical proof that is submitted by an untrusted prover. In 1998, a major breakthrough called the PCP theorem proved that reading only a constant number of bits is enough to verify any NP statement. This animated diagram illustrates the mechanism. The verifier relies on a strictly limited resource, a logarithmic number of random bits, which cast rigid projection lines down to select exactly 3 specific bit locations on the proof. This system enforces a rule called completeness. If the provided proof is correct, the specific bits queried will satisfy the verifier's checks with a probability of exactly 1. It also enforces a strict soundness rule. If the proof is false, no matter how the data is manipulated, the verifier will reject it with a probability of at least 1/2. This mechanical separation between 100% truth and lies caught at least 50% of the time provides the exact architecture needed to build an optimization gap. To weaponize this separation, we have to stop treating the PCP verifier as an algorithm and start viewing it as a physical optimization problem. Because the verifier is limited to a logarithmic amount of randomness, it can only generate a polynomial number of possible random stream choices. This maps those execution paths to a constraint satisfaction problem. Each distinct random string the verifier could generate becomes a specific constraint node in a network. The written proof itself maps directly into this system. The individual bits of the proof become the variable nodes that the constraint edges plug into. Applying the completeness rule to this graph means that for a valid proof, there is a state where 100% of these constraint nodes are satisfied. This locks our alpha gap threshold at exactly 1. Applying the soundness rule means that for a false proof, no arrangement of variables can satisfy even half of the constraint nodes. This locks our beta threshold at 1/2. The probabilistically checkable proof has literally become an instance of gap max CSP. The approximation gap is physically forged directly from the verifier's exact soundness error. We now have a massive gap in a highly specific constraint graph, but we need to route that mathematical hardness to natural problems like vertex cover or set cover. This routing is done using gap-preserving reductions. These act as translators that alter the structural layout of the problem without collapsing the space between the alpha and beta thresholds. A problem known as label cover serves as the central hub of this reduction network. Label cover is engineered to amplify gaps using parallel repetition. This highlights the resulting inapproximability factor, scaling up exponentially as a function of n. By running multiple checks in parallel, this technique drives the soundness error down toward zero. It takes the initial narrow gap created by the PCP theorem and widens it into a rigorous starting point for all other reductions. Without label cover acting as a gap-preserving amplifier, the raw output of the PCP theorem would remain too weak to bound the approximation limits of natural optimization problems. Researchers systematically calculated these amplified gaps to map the precise limitations of computational power. This network shows how label cover feeds its amplified gap outward into the classic optimization problems we initially set out to solve. Through these reductions, the best possible approximation ratio for max E3-SAT locks in at exactly 7/8. For vertex cover, researchers like Irit Enor and Shmuel Safra calculated a strict inapproximability bound of 1.3606. And for set cover, the bound stretches to the natural logarithm of n, proving that no constant factor approximation can ever exist. This brings us back to the paradox of approximation. Trying to compute a good enough solution within these bounds requires identical computational power to solving the problem perfectly. The architectural constraints of the PCP verifier dictate the hard mathematical limits of algorithmic approximation.